Siddharth Garden, for example, if you go to, you will find Gabai and Thirst to the same place causes of this era. And I've been asked to introduce we normally I feel kind of diffident at having this onerous task. But I will, in one sense, I am, as I was telling you this morning, usually they ask older people to introduce young people. And that, I can't claim that as the thing. But thanks to math genealogy, I can claim to be a sort of uncle of his. Because Du is his great-grandfather. Right? So BB to Ashok Maitra to Blackwell to whereas Duke is my grandfather, so I'm one generation closer to Duke. So anyway, BB subject is his PhD thesis was in the area of descriptive set theory, which is kind of linked to logic and kind of tongue twisters and difficult things like David's theorem that Siddharth spoke about yesterday. For example, I'll just give you a flavor of the kind of things that you see in a very simplistic flavor of descriptive set theory. On the real line, for example, you know that there are operators, and then you have open sets, which are countable unions of operators. And then you have these things which are called G delta sets, which are countable intersections of open sets. And then you can form countable unions of G deltas, or G delta sigmas. And then you can take countable intersections of those, and then countable unions of things like those. And you can keep on constructing this, and you can ask if at some stage you can all subsets of real numbers. And you will find descriptive set theory will tell you that no, this is not the case. There are sets which can never be obtained by taking finite units, countable units in intersections from integers. And so they describe the kind of complexity of sets in some sense. Okay, and from descriptive set theory, of course, he has moved on to work in the probability theory. And he has, what to do, so I would, because I knew I had to do the job, I sent him an email a few days ago. I said, please tell me what you're going to talk about, so that I can take the talk. And so let me just read out what we wrote. So he says, we shall do very basic probability of arranging balls into boxes. We shall explain the Bose-Einstein statistics from two probabilistically different views, that of Bose himself and the other mathematician Sudhakar Kunti. Then why did I not give a suggestion title like Bose-Einstein statistics? I was afraid that using big names may not keep the minds of youngsters open, even though the matters are real. So you know that you have a master who is going to tell you great things through simple ways. So thank you.
Thank you, sir, for the kind words. And thanks for the organizers for giving this chance. So today, we are going to discuss, as Sudhar already said, very simple things. Putting parts into boxes. Of course, you might ask, what is there to discuss? Yeah, but there are certain rules to obey. So, yesterday I was talking to some of the participants and also today. So it appears to me that many of the participants are not comfortable with probability. Maybe some of them think that it is too trivial and some of them think that it is too difficult. So in any case, I will start with a brief introduction. Okay, so let us see. I am going to ask a point 4 times. What is going to happen? Of course, usual point. It has heads and tails. Okay? So whenever you toss it once, either heads will come up or tails will come up. So if you toss it 4 times, that's what is going to happen. Either you will get all 4 tails, or 3 of them tails, 1 head, 1 head. or two of them are tails, and two of them are heads, or three heads, or all the four heads. Nothing else can happen. Okay? So, when you toss the coin 4 times, there are 16 possible outcomes. Okay? That is what we say. Anything that happens when you do the experiment, not an outcome. Okay? So, this set of all outcomes is denoted by some letter, whatever it is. Okay. If the coin is failed, what is meant by failed? Anyway, very good. So, heads and tails are equally likely to be here. Then, any outcome is as likely as any other outcome. Therefore, of the 16 outcomes, each of them gets probability 1 by 16. Okay? So, we will use the probability and chance. Right? So, heads had chance half when you toss once, tails had chance half. Okay? And since everything is equally likely, all the 16 outcomes have the same chance. And somehow the chances add up to 1. Because when you toss a coin, something or other happens. Okay? So, chance for outcomes are numbers which are non-negative, they add to 1. So, alright, so what do we do with that? Well, we now talk about subsets and ask questions. What are the chances of this happening? What are the chances of that happening and so on? Okay? So, for example, an event is any subset of the set of outcomes. Okay? But of course, we describe subsets in words. Okay? This is one 4 heads occur. What does that mean? That is the event which consists of only one outcome, 4 events. Suppose I say exactly 3 heads is there. Then that event consists of 4 outcomes. Okay? As we have seen, there are 4 outcomes, there are 3 heads. Okay. So probability of an event is sum of probabilities of the outcomes in that event. Okay? So look at your event, see what are the outcomes. Look at the probability of each outcome. Yeah, that's the probability of the event. For example, if the event is as I described earlier, all the 4 are heads, there will be 1. So probability of the event is. And suppose, to give another example, P is the event. At least 3 heads occur. Remember, at least. So either 3 or 4. You see that there are 5 outcomes. Okay? 4 outcomes include exactly 3 heads to there. 1 outcome includes all the 4 heads. Therefore, total 5 outcomes. And since each outcome has probability 1 by 16, this event has probability 5 by 16. Okay, what do we do? The y is not there. Okay? Maybe there is a higher chance of it appearing. That is, right? So, let us fix a number p between 0 and 1. So, p is the chances of getting x in one toss. Okay? So, for example, if p is 2/3, then chance of getting x is 2/3. Chance of getting tails is 1/3. So, x are twice as likely as tails. That can happen. Then, how will you change the probabilities now? We will make a new assignment of probabilities. For example, all the 4 stages, first is stage, second is stage, third is stage, fourth is stage. Okay? Chances first is stage 1 minus 2, chances second is stage 1 minus 3 and so on. I multiply. You ask me, where do you multiply? Well, I will answer that in a minute. Briefly. But let us do that for the time being. If you feel uncomfortable, forget about all this nonsense. Just give any numbers to the outcomes. Okay? The number that I write there covers the statistic, except to illustrate how to calculate certain things. Okay? Even if you wrote different things, you can calculate exactly the same way using your numbers instead of my numbers. Okay? Alright. So chances of H P, chances of H is P. P is 1 minus P, again P, again P, so P into 1 minus 4. So all those 4 outcomes each have probability P into 1 minus P. So that's the kind of thing. So now let us ask the same questions as this here. If all 4 are x, what are the chances to get all 4 x? That even consider that one outcome. Like for a 4 is a yes. Remember, be it the event at least 3 x. Okay? That has 5 outcomes. What are the 5 outcomes? This last one, 4 gets. And oops, this dash was 4, this is what 4. And those 4, H, T and so on, if you add those probabilities, 4 probabilities, 4 times 3 into 1 minus 3, just 24. So calculating probabilities is very simple. Okay? If you know probabilities of individual outcomes, just add. That is it. Alright. Probabilities are several interesting probabilities. Okay? Well, that's what the probability is. And you will also get more because we discuss it. Right? So, if we have 2 events with no common outcome, there is no outcome common to the 2 events. It is expressed in the perspective, A intersection B is empty. The probability of A, B and B is probability of this probability. What is? Okay? In calculating probability of A, B and B, you get all outcomes here. And your probabilities. You will do it in 2 stages. First, add probabilities of outcomes to A, then add probabilities of outcomes to B. That's it. Okay? Then add. So, it is an interesting thing. Now comes a concept that is peculiar to probability. Not just mathematics alone. What is it? Many times you do an experiment, you are not ignorant of the outcome. That doesn't mean you know the outcome. If you know exactly what happened, there is nothing to discuss about chances, okay? You know what exactly happened. You have partial information. Okay? You want to understand other events. So in the earlier experiment of crossing the point 4 times, okay? I crossed the point 4 times. I know what happened. You don't know. I am going to tell you at least 3 heads appear. I will tell you this information. Then I will have to calculate probabilities of events. So, for example, I want to know the chances that R polar heads. So let us do simple. A in the event R polar heads. B in the event at least 3 heads appear. I want probability of A given me. That particular line is simply a location. Okay, you can derivative, right? It is the chances of A given me. And suppose my point is A. There are 16 outcomes. If I tell you that B has occurred, if you still believe that all the 16 are equally likely, there is no fun. There is no meaning. Because you know that outcomes in B have occurred. Okay? So any outcome outside B must have probability 0 with this information. So just the 5 outcomes in B are equally likely. Remember, B at least 3 heads. Okay? So either 3 heads, there are 4 set outcomes, or all the 4 heads, 1 set. These 5 outcomes are not equally likely. That's it. So every outcome outside B has probability. So just the 5 outcomes will be as possible, of which only 1 outcome will be given A. Therefore, conditional probability of A given B is 1 by 5. Now, what happens now? As I explained, we have simply taken this information into account. Okay? By reassigning probabilities with the outcomes. We give 0 for those outcomes which we know have not occurred. Okay? And for those which perhaps have occurred, we will assign the same probabilities as earlier. Of course, if you assign exactly the same probability 1 by 16, that won't add up to 1. Okay? Remember, I told you the chances of all the outcomes put together will add up to 1. Signifying that something or other will should be happening. So, conditional probability of event is just a good old description. It is sum of conditional probabilities of outcomes in that event. There is no change in the definition. Now, if the point has chance of SP in each class, then what you do? No idea. Okay? Any outcome which is not in this event would get conditional probability 0. And outcomes which are in this event get probabilities proportional to what you already have. Okay? Because the total probability should be 1. But every outcome outside B, I have assigned conditional probability 0. So, for outcomes in B, I should assign its original probability divided by the total. Okay? So that the sum is 1. And here, P has probability of 2 to the power of 4 plus 4 P3 with 1 minus 2. Okay? Therefore, here is the new assignment of conditional probabilities. Every outcome outside P has conditional probability 0 because I know it is not. Any outcome in P has probability equal to earlier value divided by this 4P2 into 1 minus 3 plus 2. Having assigned conditional probabilities, you just calculate conditional probabilities of events from outcomes. Exactly in the same. So you see the probability of XXXT given to that. There is no need to go into that to calculate all this conditional probabilities and so on. Okay, but you are doing. So conditional probabilities also have several interesting properties. Really, what property? Conditional probability of the given A given P is probability of A exception P divided by probability of P. Okay? So you might ask me about we have said conditional probability is equal to earlier, now we have to do smart enough, calculate the life or what? No. There is a clear advantage in this equation. If you want to calculate conditional probability, then you do not have to go through the description I mentioned. If you have probabilities on the right side, they are just probabilities of A exception B and probability of B. So if you understand probability, you can use those to calculate conditional probabilities. You need not assign conditional probabilities to outcomes and then start calculating. Okay? So that is the advantage of this formula. That is very easy. Okay? Because if you get any outcome not in A, its conditional probability is 0. If you get any outcome in P, its conditional probability is the original probability divided by P and right. So there is that. And here is another way of writing. Probability of A exception B is probability of B into probability of A given. As you see, I have written the same equation as above. And sometimes when you write the same equation in a different form, that will help in calculating certain things. Right? You will see that. Suppose A1, A2, AK are disjoint numbers, then the conditional probability of the union is summation of the conditional probability. Again, nothing to. Okay? So conditional probabilities also add up, just like usual probabilities. If you have disjoint events, again, when I say 2 events are disjoint, that means there is no outcome in common. Okay? All right. When do we say that 2 events are independent? If the chances of A, with the information that we have obtained directly, it is same as earlier chances. That is, the conditional probability of A given B is same as probability of A. That means the information that we obtained did not play any role. Therefore, it is reasonable to say A and B are independent. Suppose you take a deck of cards. I ask you what are the chances. You pick one card at random. There are 22 cards, right? What are the chances that the card picked is ace? It is 4 out of 30. 1 by 30. Good. Suppose I tell you I picked a card. It is diamonds. Tell me, what are the chances there is? So I am telling you that the card picked is diamonds. And I ask you what are the chances there is? Will my answer clear? No. There are 13 diamonds. So what is the chance? So it is again 1 by 30. That the card picked is diamonds did not change the chances that it is. So when that happens, we say that the events are independent. Mathematically, probability of A exception B, probability of A, probability of B. Okay, that is the value. See what I said in verse above. Because P of A exception I P if precisely the condition is probability. Okay? Alright, when you say that 3 events are independent, if the chances of the event are given any event I can put together. Alright. When you say that k events are independent, well, probability that any one of the events happens, given information about any other. Okay? For example, you can ask the chances of A1 given A2 happened, A3 did not happen, A4, A5, A6, A8 happened. What happened? You should be saying that the condition. Okay? When that happens, when you say that the events are independent, any information about any of them will not tell you about the other. Okay? And this translates to mathematics in the following. If you get any subcollection of the events, for example, if you take A1, A3, A2, probability of intersection is the product of probabilities. You can show that mathematically whatever I said in words about it precisely. But otherwise, there is no need for us to do that. The only reason I did that is for the following reason, for this calculation. For the point passing, the chances of S is big. Why would we associate probabilities with the way we did? Well, this is the only way to associate so that the following 4 events, AI, ith class results in S. What is A1? A1 is the event, first class results in S. That consists of A outcomes. H. Other three variables. A2, the event is the second class results in S. That consists of A. Second is the first, third, fourth variables. These events, 4 events are independent and each event has probability. This is expressed by saying that we are asked to find independent. So that is why I multiply. Okay, have it right. All right. So now let me come back to the question. I said we are going to distribute 1 to 1. All right. For the rest of the lecture, this is going to our main theme. We want to distribute 1 box. I have 4 boxes. And I have 2 boxes. I want to distribute them. And I have a coin. Chance of getting a toss is big. For each ball, I toss the coin. Heads up, I put it in box 1. Tails up, I put it in box 2. So I get the ball, toss the coin, see what the coin tells me to do. I will put the coin. Okay? Think of heads in box 1, tails in box 2. I take the second ball, again toss the coin. Remember, okay? Do the same. Third ball, again toss the coin. The question I am interested in is how many balls are in box 1? Of course, the number of balls in box 1 is either 0 or 1 or 2 or 3 or 4. What are the chances it is 3? Well, the chances it is 3 is similar to the chance that you get exactly 3 hits. Whenever you get a head in box 1, exactly 3 hits. What are the chances of getting exactly 3 hits? It is big 2 into 1 minus 2. 4 times. Because any outcome which has 3 hits exactly has probability 2 into 1 minus 2. There are 4 such outcomes. Therefore, 4 times 2 into 1 minus 2. Okay. Similarly, the other. What are the chances? There are 0 balls. That means all of 4 chances but 2 hits. 1 minus 2 into 1. Okay? So very simple. Nothing problem. Okay. Nothing very good. Life is really getting complicated. I have 2 coins. Not 1 coin. What I do is the following. I pick 1 coin at random. I do the same thing as I did yesterday. Okay? Remember, I am not going to pick the coin forever. Once I pick up the coin, I move that coin to distribute the 4 parts exactly as I did earlier. Okay? I am not going to pick up 1 coin for each one. So there are 2 coins. I pick up 1 coin, that's all. I use this coin for other people. Okay. What are the chances? I ask the same question. What are the chances that there are k balls in box 1? I say this is the answer. How? 4 to k. P would be for a k, 1 minus q for a 4 minus k. Listen. Why is that so? Well, that is profound. Suppose I denote by event A, the event K balls in box 1. Okay, if you don't like that K floating around, think of 3 balls in box 1. It's very good difference. P1, point P1 is selected, P2, point P2 is selected. I say the event A is the union of the two events A and P1, A and P2. Why? Because P1 is the event, first point is selected, P2 is the event, second point is selected. Okay? You are going to select one of the 2 points anyway. So either we will have one, you have. Okay? Both will have. So the event A is this one union of those 2 and then this one. But now we have made section B1 is P of B1, it is P of A2. Okay? One condition problem. What is P of B1? I said I select points at random. If the point had come out of the select, half it will be a break will be 1. What is probability of A given B1? It is 4 to A, P1 to the power of A, into 1 minus P1 to the power of 4. Because given P1, you have a point with chance of X P1 in your hand. You are passing it 4 times. What are the chances of getting exactly Kx? That's it. You can. Similarly, we have other. Okay? Let me complicate like a little more. Chances of X, I have 3 points now. Okay? 3 points. So I pick one of the points at random and do the same. The question I asked in the same, what are the chances of getting 0 balls in box 1 ball in box 1? I take each chances of getting a ball in box 1. Why is that so? Exactly as in here. Suppose you do not like E1, point 1 is selected, point 2 is selected, point 3 is selected. Then the event A is the union of the sub-events A and B1, A and B2, A and B2. Therefore, all is set. Exactly the same. Okay? 1/3 is probability of B1. And 4 square, P1 to the power of K, 1 minus P1 to the power of 4 minus K is the probability of K given. Similarly, P2 similarly. Alright. I have 99 points. Then what? Okay. Now, instead of getting complicated, like to get it good. So what do we do exactly? In step 3, we have 99 points. So I will decide 4 to 1 by 99. Now, life gets really complicated. Imagine I have a bag full of points. Okay? How many points? For every number 3, 2, 0 and 1, 4, there is a comma here. 0 less than 3 less than. Okay? For every number 3, 2, 0 or 1, I have a point in my bag. What is the property of the point? If you toss it, chance of persistence. Okay? Rule. Pick a point at random and use it to place all the points. I have no pass. I am going to place it with the boxer. So I pick a point at random. Okay? So instead of 99 points or 100 points, I have plenty of points. 1 point per every number is lower. What is the property of the point? If you toss it, chance of persistence. Okay? Alright, now this large thing will come on. We have done that. We never have so many points. Sure, we never have so many points, okay? Not with independent we let go something. But I only said man, I never asked you to do it. So, and moreover, if you still object, why do you imagine something I can't do? Well, in fact, most of the functions in mathematics, like this, let's look at going up there. He's borrowing 200. What was it doing? Probably he is taking a run of 41 miles per hour and then releasing the bar at 60 miles per hour. Of course, in the same direction. Therefore, the addition will have large power and this will have large 101. Okay? When we back to the TV, these two are not separate though. I don't know why. But anyway, that's what is that. Isn't it? Okay, now let us see. It's a great what to imagine. The same goes of that. Taking a 100,000 miles per hour car and releasing the bar with 100,000 miles per hour. What happens to the bar? It's a nice thing to think about it. Anyway, we will not discuss. Now, you may think that my answer is very flippant. I have not answered your question. So let me answer. You did not have so many points. After all, you have points. You begin upper at random to be 0 to 1. Just have 1 point which consequence in that way. Because I am going to use that isn't it? I will never return to my bag of points. Therefore, you select a number P at random with 0 or 1. Just take a point to consequence. P. Use that point. 4 points. Okay, so let us get back to our problem. Now that we will be sensible. Okay. Chances of K bars in box 1 is what you say. You can assume fit for 1 minus 2 for 4 minus 3. Here we are. I was taking average. Now I have taken each of them. Okay? Alright. Why did I do that? Well, if you recognize the earlier answer was clearly demands, okay? You look at the function, this is based 1 minus 2 to the power of 4 minus 3. You took its value at certain points, you will be whatever you have, and you the average. They are the answers, approximately. Therefore, for this imaginary problem, which is the limit case of the earlier problem, the answer is this one. It is very nice. Now, if you do not like this explanation, unlike school, where the teacher says something that you have to accept. Here, you are under no compulsion to accept anything that I say. Okay? So, it is important that you should be convinced. Let us go back to this. Basics. A is K bars in box 1. B is point P is selected. The event A is still union of all these sub-events, A and B. That is still. But now there are too many events whose union is E. I cannot apply the same as in there. I cannot add up all the probabilities. There are some problems. So addition is now replaced by D. Of course, you may not like this explanation also. Possible. You might say, come on, you said the same thing in different words. You didn't say different. Okay. But then I only say you need to understand analysis of experiments. Too many outcomes. Okay. Selecting a point, there are too many outcomes. We can never be attached to the one. Okay. So if you go through that, then you will get the answer. So let us accept that. The above integral that equals 1 by 5. Good. And it's not difficult. You just integrate by parts, okay? 0 to 1, 3 to the power of 10, 1 minus 2 to the power of 4 minus 3. Suppose, for example, k is 4. What is that? It is just 0 to 1. 2 to the 4, that is 3 to the 5 minus 1. Okay? Suppose k is 3. It is b2 into 1 minus 3. Integrate by parts. Okay? So, we are in a beautiful situation. Life got very complicated. We have too many points. But then, chances of K balls are 1 by 5. Moreover, if you pick a random point and distribute the balls, then the chances of K balls in box 1 is 1 by 5. Whatever we get, so of course, I could have qualified it. Whatever we get subject to the condition, it is either 0, 1, 2, 3, 4. Okay? We check probability number, but other equal like that. Okay. So, it left you a beautiful answer. Now, keep it aside for a moment. We'll get back to this. This is the rule. I now mentioned earlier. The 4 parts look alike. So forget about what we have done, okay? I will now think of a different experiment. I have 4 bars. I tell you that all the balls will collide. Okay? You can't distinguish one ball from the other. I won't allow you to put marks on the balls. Okay? They all will collide. All the arrangements of the balls that your eye can distinguish are equally likely. I have made you two rules. One, the balls will collide. Two, if you look at all possible arrangements that your eye can distinguish, there are equally likely. Now, what are the arrangements now? Exactly 5 arrangements. Box 1 has 0 box, box 1 has 1 box. No arrangement. Because the balls look alike, it doesn't make sense to ask, did you put the first ball in box 1 or the second ball? It doesn't matter. First ball in box 1, 2, 3, 4 in box 2. That is one arrangement. Third one in box 1, balls 1, 2, and 4. What is the other box? So that's it. Your eye can't distinguish. Okay? So, the only thing your eye can distinguish is how many balls are in the box. No more. Which balls are there is a meaningless question. Okay? So, there are exactly 5 arrangements. There are equally likely. Beautiful, isn't it? So, if you make this rule, you end up with the same answer. Okay? Suppose I have 100 balls instead of 4. I make a rule. K. Remember what is K? I select a number P at random from 0 to 1. Okay? And use that P to distribute all the 99 balls. Okay? Oh, 100 balls. Okay. Then, how many balls are there in box 1? Well, instead of 4 balls, there are 100 balls now. So, in box 1, there could be 0, 1, 2, 10 balls. Each has probably 1 by 100. Okay? Sorry. Yeah, 1 by 100. There are 100 and 1. Okay, there's nothing profound here. You see, now mathematics makes so detailed that what you don't have to do, right? Instead of 4 choose A, 3 to 4 up to etc., you have got 100 choose A. Exactly the same thing. So you do that. We have 2 models here that you say imagine that the 100 balls are actually photons. So they are not boxes. And boxes are actually electrons. Okay? So, photons are trying to occupy this field. There are 100 photons entering into this hall. There are 2 electrons. They want to get fitted into holes. How do they do it? Okay. Rule B is what SN Bose proposed in 1954. If that's the truth. If 100 photons are trying to occupy 2 states, this is how they do. One way of doing the following, they collectively pick a point. Each one follows what the point dictates to do. Okay? They all pick up one point. Then each one passes the point and decides what. Or, here is another way of describing the same thing. The photons behave like particles looking alike. Okay? There is no distinction. They all collide. And they pick one arrangement at random and follow that. Okay? This is SN Bose. And he has proposed this and then derived the Planck's radiation law. We tried to publish it, but of course, nobody accepted it. So he wrote Einstein. Respected sir, I have ventured to send you a accompanying article for your pleasure and opinion. I am anxious to know what you think of it. If you think the paper worth publication, I shall be grateful to arrange for its publication to next. Though a complete stranger to you, I do not hesitate in making such a request because we are all your pupils. So profiting from your teachings, your writings. It goes on to say that he is the one who translated his book on derivatives, quantity, and then Einstein himself translated and submitted to this author. In my opinion, what is referred as the Planck formula signifies an important advance. The method used also yields the quantum theory of the ideal gas as a result. So he translated. It is lower mechanical science. Acid versus work on particle statistics, which clarified the behavior of photons and opened the door to new ideas in statistics of microscopic systems that obey the rules of quantum physics, was one of the top 10 achievements of 20th century Indian science, and it is considered the Nobel Prize. Now, why did this idea revolutionary? Why did they not publish it further? Okay? This was classified as a high school mistake, you see, essentially. This was against conventional wisdom. Why? Why did it go against? Well, suppose I have earned 1 red ball and 99 green balls, okay? I tell you all the green balls which are right. Okay? Then you will pop 1 red ball, 99 green balls, and all the 99 green balls will be correct. And I will tell you, if I try a ball at random, I will ask, suppose the outcome that your eye can distinguish are equally right. Does it make sense? What your eye can distinguish? I think the red ball and green ball. Why not? All the green balls will be right. It doesn't make sense to ask 2 green balls to draw. Okay? So there are only 2 outcomes that your eye can distinguish. Therefore, you would be saying chance of red ball is half, chance of green ball is half. It is 2 nonsense, right? Your box has 1 red ball, 99 green balls. So proposing this and saying that these outcomes your eye can distinguish are equally likely is against the conventional wisdom. Nobody can accept that in this case chance of red ball is half the chance of green ball. But you can't help it. That is how photons do. What can you do about it? Okay? Nobody understood that aspect. Because Einstein who understood. Oh, what if there were n balls? I was all the time saying 4 balls, 100 balls, 100 balls. What if there were n balls? Exactly the same thing. A little more boring details. The number of balls in box 1 is either 0 or 1 or n. We will probably do not by n plus 1. Okay? Either you can follow with K or you can follow with B. You get the same answer. Okay, let's make it a little more lively. What if there are R boxes? So there are 10 photons coming into this room. I put R shapes here. They want to sit on the shapes. How is it? Instead of shapes, there are R shapes. Well, to apply will be every arrangement is determined by the occupancy numbers N1 and N0. Let us keep the same rule. Big 10 photons or whatever, they will be aligned. The arrangements that your eye can distinguish are equally likely. What are the possible arrangements? Well, all possible N1 and 2 N are tuples, non-negative integers adding up to N. Okay? The only way that distinguishes one arrangement from another arrangement is the number of balls in box 1, box 2, box R. Okay? It makes no sense which ball went where again. So it is only those numbers that distinguish one arrangement from another arrangement. Therefore, the possible arrangements now are those articles. Okay? Whenever I write an article now, think of it as N1 balls in box 1, N2 balls in box 2, NR balls in box R. That is what that arrangement is. Okay, how many such arrangements are there? There are n plus r minus 1 to the r minus 1. Okay? And they all have equal probability. So each has probability that way. And why are there so many arrangements? Well, I won't convert it to a class probability, but I will quickly explain to you. You put n plus r minus 1 star marks in a row. Okay? You select r minus 1 of these stars and make them into vertical lines. So I have selected the third star, made it to a vertical line. I have selected one more line. If you look at the picture down, what do you see? You see 4 boxes. Below, before the first vertical line, between the first and second vertical line, etc., and after the last vertical line. Okay? You see 4 boxes. And how many stars are remaining? Initially there were n plus r minus 1 stars. I have taken r minus 1 star, or n star. So if you look at the picture below, you will see r boxes and n stars put in the r boxes. Okay? So here, for example, there are 4 boxes if you put n plus r minus 1 stars in a row, select r minus 1, make it into vertical lines, you will get one arrangement of the ball into the box. Any arrangement occurs in this way. So I give it to you. So there are so many things. What about rule K? Okay. Rule K now is as follows. The n photons collectively pick an arc face die. Okay. So as they enter the room, there are all dice kept there. They pick up one of the dice and enter the room. Then each photon rolls the die and goes to the corresponding place. Similar analysis, except for technical details. A coin is represented by one number if you know the chance of this. A die or base is represented by r minus 1 number, and r plus die is represented by r minus 1. P1 into r minus 1. What are those numbers? P1 is the chance of getting place 1 when you do the dice. P2 is the chance of getting place 2. P r minus 1 is the chance of getting place r minus 1. Okay? What happened to arc face? Well, that is 1 minus P1, etc. So, okay? The remaining problem. When equation 1 or summation pair is extended. Exactly the same calculation, you need to use multiple integrals instead of taking how you answer. There is nothing wrong, okay? It is only a technical detail. There is no idea involved in it, okay? Rule K is by the statistician Sudhakar Kunde, a couple of years ago, disappeared in Shankya. But of course, if you ask physicists, perhaps even physicists have their own favorite inventor. This seems to have been discovered by several people. But as far as I know, first appeared in 77. Okay. So now, Einstein asked the following question. Fantastic. These particles are looking alike. Why don't I apply Bose's idea with Bose's principle? See what happens. Okay. So let me tell you what is Bose's principle now. Okay. Oh, this is for particles. Okay. Now I will tell you. So far I was telling photon and so on and so forth. Okay. So particles should obey the principle that both outside are not photon, for example. And we wanted to do two things. Number one, apply Boltzmann's principle. Number two, apply not to photons, but to particles of matter. Okay? Now, matter has a technical meaning in its community. So, it is something that has a rest mass and outside volume and so on. But photons don't have mass and so on. So that is why it is irrelevant for us to understand what it is. Okay? Here you can do at this moment, let us say that photons or whatever which obey those principles are being discussed. That's okay. If a system is equilibrium, the word equilibrium, forget it. Okay? See, if you want to describe a system which will solve theory, okay, it's very complicated. You have to wait until it comes to equilibrium, then you discuss what happens. So, forget about what you do. If you tell me in one of A states, 1, 2, A, if error is even K, the probability that a system in the state I is proportional to e to the power of minus EI divided by some. Okay? Because of that. E is separated, combine the Boltzmann constant. But the point is, the chances that it is in the state I is proportional to e to the power of minus EI. As K becomes large, this becomes small. Okay? So higher error is a smaller probability. So, this is the fundamental law, and then you derive several consequences of it. Okay, now let us see what happens if we apply. You guys look at n particles of matter, but number two, apply not to photons, but to particles of matter. Okay? Now, matter has a technical meaning in its community, so it is something that has a less mass and oxidize volume and so on, but photons don't have mass and so on. So that is why it is irrelevant for us to understand what we have described. Okay? Anything to do at this moment, let us pretend that photons or whatever which obey those principles are being discussed. That's it. Okay. If a system in equilibrium, again, the word equilibrium, forget it. Okay? Because see, if you want to describe a system which keeps on changing, okay, it's very complicated. You have to wait until it comes to equilibrium, then you discuss what happens. So, for example, if you tell me in one of S states, 1, 2, 8, if energy is evenly decay, the probability that the system in the state I is proportional to e to the power of minus ei divided by some bucket. Okay? Because T is temperature, apply the Boltzmann constant. But the point is, the chances that it is in the state I is proportional to e to the power of minus ei. Okay? As ei becomes large, this becomes small. Okay? So higher energies have smaller probabilities. So this is the fundamental law. And then you derive several consequences of it. Okay, now let us see what happens if you apply. Okay, imagine, go back to n particles of matter, but don't think of again R energy levels, keep it aside. Again, let us look at the simpler situation. As earlier, two energy levels available. Alright, let us now give name to those two energy levels, E and E plus epsilon. Okay, epsilon is important. Now, there are n plus 1 possible configurations, isn't it? That's what we saw. Okay? Namely, determined by how many are sitting on the chain E plus epsilon, right? There is a chain E plus epsilon, all the photons are sitting on the two phase. Okay? And configuration K as energy and E plus K epsilon. Why? Because what is meant by configuration K? That means K particles are sitting on chain E plus epsilon. Therefore, the total energy coming from there is Ke plus K epsilon. N minus K particles are sitting on the chain E. So the energy of this is N minus K times E. Add up. The total energy is N times E plus K epsilon. Right? Okay. So Boltzmann says that the configuration K has chance proportional to that energy. Okay? You see some Greek symbol beta there. That 1 by kappa t has disappeared. I replace it by some constant. Forget about the constant. You don't have to pay any attention to that. It's proportional. When I say it is proportional to that, what is the probability of this state K? Okay? Configuration K has probability. This number I have written there divided by the total sum. That is the probability. Right? Total has to be 1. Therefore, probability of the configuration A is that number divided by the sum of all those power T. Now, we have a beautiful exponential function which e to the power of minus beta n E is common from both numerator and denominator. That cancels out. So, probability of this configuration A is actually e to the power of minus beta k epsilon divided by the summation of e to the power of minus beta k epsilon. That's it. Power k 0 k. Right? So, if you know e to the power of minus beta epsilon by p, then the number of particles in chain e plus epsilon equals k, the probability p to the power of p. Okay? P is e to the power of minus beta. Okay. So, chances of having k particles in state e plus epsilon. So, what is the expected number of particles? Until they are not as Matthew was telling us, expected you multiply the number by a probability and add up. So whenever you say probability of something happening, that means a proportion. So that is why. So okay, without going into details, why expectation is defined in that way. Okay, expectation of a random variable is value multiplied by probability. So that is what I do. Summation k multiplied by probability is p to the power of k by c. If the number of particles is very, very large, then this sum can be approximated by this infinite sum. You know, Cn is 1 by 1 minus p. Therefore, 1 by 1 minus p, the denominator, that becomes 1 minus p, summation kp. But you know how to calculate the infinite sum state. It is 1 by 1 minus p whole square. Okay? Very easy. Therefore, it is 1 minus p, it will be 1 minus p whole square. That is what the expected number of particles. I would like to notice that this does not depend on matter. Okay? I am not saying that if there are n particles, half are in this state. Okay? Independent of n, I am saying so many particles are on this state. No matter what it is. So what's happening? Majority of the particles are sitting on the same heap. Isn't it? Only very few particles are sitting on the same heap as epsilon, right? These are expected number of particles in different sizes. Not proportional, right? This does not depend on n. If you put a half n or something, jump by 10 times 10, then you can say the proportion 1 by 10 is here. And you will get, no? Independent of that. That is the profound. Now let us use some jargon. Okay? It's always fun to use jargon for doing it. State with lower energy, let us call it ground state. State with ground state. State with higher energy, let us call it excited state. Then, Einstein's prediction, a collection of enough Bose particles which force to be